In this next module, we're picking up where we left off in the last chapter, the last module, excuse me. We were doing all kinds of different transformations. We were rotating things, we were reflecting things, we were translating things. And so now in this module, we're starting by doing sequences of transformations. So in the explore activity that your text describes, in part A, you see it says, using geometry software, draw a triangle and label the vertices A, B, and C, which you see that I've done here. Then draw a point outside of the triangle and label it P. It says, rotate triangle ABC 30 degrees around point P. Okay, so in order to do that, I have to tell the program that I want P to be the center of my rotation. And then I'm going to take this figure and rotate it, but I don't want it around that angle by 90 degrees. I wanted 30, and there's my rotation. And it says label that image as A prime, B prime, and C prime, and when I tell the program to label my points, it automatically calls them that. Then it says rotate this triangle now by 45 degrees around point P. Okay, so I'm going to tell it that that's my center again. And I'm going to rotate this, but not that or that. And I'm going to rotate it, like the activity said, by 45 degrees. And your text says to label that image as A double prime, B double prime, C double prime. And look at that. Program knows already what I want those points to be called. And then in part B, it says to make a conjecture regarding a single rotation that will map triangle ABC to triangle A double prime, B double prime, C double prime. So what I'd hope you'd kind of have a gut instinct about is that if I had started at triangle ABC and done a different rotation, I would land at A double prime, B double prime, C double prime. So let's test that. Let's take this triangle and rotate it by, well, my first angle was 30 degrees, my second angle was 45 degrees. So if I add those two things together, then where does it land? Well, notice that it's highlighted this again. Well, that's because it landed there once again. So what we just noticed is that rotating triangle ABC 75 degrees maps it to triangle A double prime, B double prime, C double prime. And we did that. In part C of that explore activity, your book says using geometry software, draw a triangle and label the vertices D, E, and F. So I need to open a new sketch and make a new triangle this time. Okay, so I've made my points. Now I connect the dots. There's triangle DEF. It's asking me to draw two intersecting lines and label them J and K. that. Okay, so here's a line, and there's a line. And J and K are their names. It says reflect triangle DEF across line J, and then reflect that image across line K. Okay, so in order to do that, I have to tell the program to mark the mirror. So I'm telling the program this is my line of reflection, and I'm taking this triangle and I'm reflecting it. Okay, so now it's over here, and my program is very nice to me. It knows exactly how I want it to label the triangle. And now I'm going to reflect this over line K. So now I need to tell the program that K is my mirror. And I'm going to reflect this triangle over that line. And it's D double prime, E double prime, F double prime. And now finally, it's asking us to notice a relationship between triangle DEF and triangle D double prime, E double prime, F double prime. Okay, so in the last example where they wanted me to make a conjecture or an educated guess about what happened, I had done 2 rotations, and I conjectured that if I did a rotation of the sum of those angles, I would land in the same place. So this time I did 2 reflections, and I'm trying to think of one transformation that would have the same result. So one thing that I'd like you to notice is remember that way back in Module 1 when we talked about how to look at a figure and determine whether it's been reflected or something else, is if the orientation of the graph has been changed. Meaning, for example, in this triangle, if I'm going counterclockwise, starting at D, it's D, E, F. Now, if I go to my double prime triangle and I start at D and I'm going counterclockwise again, it's D double prime, E double prime, F double prime. So since that order didn't change from this triangle, DEF, to this triangle, my double prime triangle, that's not a reflection. Well, it's not a translation either, so let us consider a rotation. But around what angle? Let's make some educated guesses. Maybe if I take this triangle and I rotate it around this point using this angle measure, it'll land here. Okay, well, first let's measure that angle. So X, Y, Z. And when I take this triangle and I rotate it, that angle, oh, that doesn't work. So I'm not even going to finish that rotation. Let's measure this angle. And try to rotate this triangle around that angle. And oh, that's definitely not it. Okay, so I've exhausted some of my educated guesses so far. So let's go back to what we did in the last module. In the last module, we connected a point to the center of the rotation, and then we connected the image of that point to the center of that rotation, and then we measured the angle. Okay, so let's measure that angle. So my actual angle of rotation is 116.41. Well, there's got to be some relationship between the angle formed by the intersecting lines and this angle of rotation. So I wonder if I use my calculator. I have a hunch that if I double this angle, well, hey, look at that. Okay, so now if I do the rotation on that angle, notice how it pops back up at this triangle. So that's my conjecture. So the single transformation that would map triangle DEF to triangle D double prime E double prime F double prime is rotating triangle ABC an angle twice the measure of the intersecting lines maps it to triangle A double prime, B double prime, C double prime. And that's what we did. And then in your book, it has 2 reflect questions that kind of ask the exact same thing that we just observed. In part B, we observed that if we add the 2 angles of rotation, we can get the 1 angle of rotation that will map triangle ABC to A double prime, B double prime, C double prime. In question 2, it's asking you in general, what do you do when you're reflecting something over 2 intersecting lines? The one transformation that's equivalent to that would be a rotation of an angle measure that is twice the angle formed by the intersecting lines. So now in this discussion this discussion question, it says repeat step C, but make the lines parallel instead of intersecting. All right, so let's come back here. And I'm going to get rid of this triangle. And I've got a few extra things that I don't need, so let me get rid of them. And I want a line that's parallel to J this time. So I'm going to tell my program to construct through this line, through this point, and parallel to this line, construct a parallel line. So now I've got parallel lines, okay? So when I'm going to call this line K. When I reflect this triangle over line J, it lands here, and I'm going to take that triangle and reflect it over this line. And now it's here. And this is E double prime, D double prime, F double prime. So I started with reflections, so it'd probably be a good idea to make sure that this isn't a reflection. So remember our test, if I take this triangle and I name the vertices going counterclockwise starting at D, it's D, E, F. If I start at this triangle and go counterclockwise starting from D, it's still D double prime, E double prime, F double prime. So it is definitely not a reflection, and it looks like it's kind of facing the same way as this triangle, so it looks like it's a transformation. So we think about transformations in terms of direction and distance. So let's consider the line connecting F prime to F, or the segment connecting them. So let's draw that segment and see if there's anything interesting about that segment and my parallel lines. Well, it looks like I might have a very special kind of angle here. Let's check. If I measure this angle, oh, it's 90 degrees. So that means that it traveled in a direction perpendicular to my parallel lines. Okay, well, how far did it travel? So let's find the length of F to F prime. And, how far away are these two parallel lines? Does my program have a nice, nope, it doesn't have a nice way to measure the distance between two lines, but the distance between them would be a perpendicular segment, so I'm just going to draw a perpendicular line and then measure the length of this segment and then find its length. Well, they're not the same, but once again, I'd hope that you'd notice, oh, there's an interesting relationship going on here. The triangle traveled a distance that is twice the distance between the two parallel lines. Okay, so make a conjecture about what single transformation will now map triangle DEF to D double prime, E double prime, F double prime. And it's going to be a translation. Try translating the triangle twice the distance, between the parallel lines in a direction perpendicular to the lines. And that will map triangle DEF to triangle D double prime, E double prime, F double prime. So in example 1, part A, as usual, there's an example where they're going through the process and showing you what they did. So in this part A example, they're doing a reflection over line L and then translating it along the vector V. So they took the triangle ABC and reflected it, and it landed here at A prime, B prime, C prime. And then the next step was to take that triangle and translate it along the vector that was given to you, vector V. So notice how I could take this vector and that's how far B is from B prime, and A is from A prime, and C is from C prime. So that's what they did. In this example, we're being asked to do a rotation, then a translation, and then a reflection. And I wanted to make sure to do this hands-on in this video because there's no coordinates in this diagram. There's no numbers. So it's a little bit different than doing it in examples that I've shown you in the past. So let me make this a little brighter. Okay, in order to apply the rotation, I'm taking this triangle and rotating around this point. But I mentioned earlier I don't have any coordinates. So let's make some. Since P is my center of rotation, I'm going to treat that point P as if it is 0, 0. You're allowed to do that. And what I'm going to do is, since the problem says to rotate this 180 degrees, remember that I showed you that one of the ways that you can do a rotation is to actually physically pick up your paper and turn it 180 degrees. So I turned it 180 degrees. And now it looks like this. And if I think of this as having an XY axis now, and I flip it upside down and I try to consider what the coordinates of A, B, and C are now, well, then A prime would now be at -1, 2. B prime would be at 1, 1, 2, 3. And C prime would be at 1, comma 0. Okay, so if I'm considering point P as the origin, this is where these points would lie with respect to that origin. So now let's bring it back to what it normally looked like. And let's take these points and plot them on this grid that actually doesn't have any numbers, but we're treating it as if this is a y-axis and this is an x-axis. So we're treating it as if P is the origin. So -1, comma 2. This is where the point A prime would be. 1, comma 3. This is where the point B prime would be. And 1, comma 0. This is where the point C prime would be. So hopefully this is a strategy that you can use yourself if you're ever asked in the coordinate grid to do a rotation around a point that isn't the origin. Just draw a pair of axes through that point, treat it like the origin, spin the paper around, figure out where the points are with respect to that not quite origin, bring it back to normal, plot the points where they would apply to that origin, and then identify their actual points. Okay, so now that's my A prime, B prime, C prime. And now I have to do a translation along this vector. So I want to take this vector and translate each of these points along that vector. Well, some of you might still be in the habit of taking this vector and physically copying it, and copying it. But in this example, let's go ahead and just count the spaces. So 1, 2, 3, 4, 5 to the right, and up 1. Okay, so from here, 5 to the right, and up 1. Here is C double prime. 1, 2, 3, 4, 5, and up 1. There's B double prime. Finally, A prime. 1, 2, 3, 4, 5, and up 1. There is A double prime. And then finally, I'm going to take this triangle and reflect it over this line. So since C is one space above it, since C double prime is one space above it, C triple prime will be one space below it. B double prime is 1, 2, 3, 4 spaces above it, so B double prime will be 1, 2, 3, 4 spaces below it. Here's A double prime. It is 1, 2, 3 spaces above. So 1, 2, 3 spaces below. There is A triple prime. In these reflect questions, we're being asked, are the images you drew for each example the same size and shape as the given pre-image? Yes, they were. In what ways do the rigid transformations change the pre-image? They change, or they may change, the orientation of the shape. Does the order in which you apply the transformations make a difference? So test your conjecture by performing the transformations in part B in a different order. All right, so in this part B, if I had done things in a different order, for example, if I had done my reflection first, then it would be here. And here. So that would be A prime. This would still be C. Let's call it C prime for clarity as well. And this would be B prime. So I've done my reflection. So let's do the rotation next. If I rotate C 180 degrees, or C prime, 180 degrees around the point P, here's C double prime. Here would be A double prime, and here would be B double prime. And then finally, if I took those and translated them along the vector V, I'd be moving them 5 spaces to the right and up 1. So 1, 2, 3, 4, 5, and up 1. Here's B triple prime. C double prime goes 1, 2, 3, 4, 5, and then up 1. And A double prime, 1, 2, 3, 4, 5, and up 1. Here's A triple prime. So how does that compare to where it landed in the last example? So if we compare the location of A triple prime, B triple prime, C triple prime, when I changed my order of transformations to where it was originally, we see that the order does matter. So you want to make sure that you are performing these transformations in the order in which it's described to you. So to answer this question, yes, the order does matter. For part B, describe a sequence of transformations that will take A double prime back to the pre-image. It's asking us what would I have to do to A double prime, B double prime, C double prime in order to land it back at its pre-image. And what I'd hope that you'd realize is that transformations are almost like equations. So think about what you do when you're solving for x. You're doing the opposite of what's been done to x. Similarly here, if I want to get back to my pre-image, I would do the opposite of what had been done. So in the opposite order, of course. So since I'm talking about what I would do to this triangle in order to bring it back to the original, let's go backwards. I would do a translation, not along this vector, but along kind of its opposite vector. Notice the difference. Its magnitude, or its length, is the same, but it's going in exactly the opposite direction. So I would do that translation, and then I would do a 180-degree rotation. So I translate the triangle along a vector opposite of V, and then a 180-degree rotation around P. In this example, we're doing a reflection and then a 90-degree rotation. And again, like the last example that I did here, there's no numbers. So we have to kind of create our own, but we'll get to that. First thing we're doing is taking this triangle and reflecting it over line L. When I do, here will be C prime, here will be A prime, and here will be B prime. To clarify, Notice how C is one space to the left of my line of inflection. That means C prime will be one space to the right of it. Similarly, A is 1, 2, 3 spaces on the left of A. That means A prime will be 1, 2, 3 spaces on the right of it. B is one space to the left, B prime is one space to the right. And now from here, I'm going to do a 90-degree rotation around point P. And like I said in the last example, since I don't have any numbers, I'm going to kind of create them. And by doing so, I have to start off by making this point kind of my origin. So I'm going to take this and turn it 90 degrees around point P. So I'm physically turning my paper 90 degrees. And when I do, this C prime would now be at negative 1, 1, 2, 3. So that's where C double prime is going to be with respect to this point. A double prime is at negative 1, 1, 2, 3, 4, 5. B double prime is negative 1, 2, 3, 4, 1, 2, 3. And so now I turn my paper back around properly, and I plot these points on my actual grid according to where P is normally. Okay, so C would be at negative 1, 1, 2, 3. So this is where C double prime is. A double prime is at negative 1, 5. So here's A double prime. And B double prime is at negative 4, 1, 2, 3, 4, 1, 2, 3. So there's B double prime. And when I connect the dots, that is my final answer after the reflection and rotation. In the next kind of examples, now we're combining non-rigid transformations. So remember that translations, rotations, reflections, these are all rigid transformations, meaning your pre-image will be the same size and shape as your image. Whereas a non-rigid transformation, sometimes it's a dilation. Notice this vocabulary. And when we talk about the word dilation, what we're saying is that it's the same shape, but not necessarily the same size. And when we talk about its factor, sometimes we might see the word scale factor. That's basically what we're multiplying the coordinates by, or eventually the lengths by. Okay, so that scale factor, or that factor, is telling you how much bigger or how much smaller this dilation image will be. So in this example that they've done for you, they started at ABCD, and then they applied a dilation in order to get A prime, B prime, C prime, D prime. You see that on the right side of your screen also. And then they reflected that over the y-axis. You see it now on the left side of your screen here. A double prime, B double prime, C double prime, D double prime. And then finally, the last thing they did was translate it. So that's your final answer on this example. This one here. So let's do one like that. The first transformation is a, they want us to figure out whether it's a horizontal or vertical stretch by a factor of, and there's a number that they want. So notice what the first transformation is that we're doing. We're multiplying all of our x coordinates by 3, and we're leaving our y coordinates alone. So since it's our x coordinates that we're multiplying, and x is a horizontal distinction, it's a horizontal stretch by a factor of 3. So let's apply that stretch. Well, in order to do that, let's identify our coordinates. A is at 0, comma, -2, B is at -2, -4, and C is located at -4, -4. When I apply that stretch, A prime is still here, because when I multiply 3 times 0, it's still 0, and I'm leaving the y-coordinate the same. B prime is at -6, -4, here. And C prime is at -12, -4. Here. And we label that image naturally A prime, B prime, C prime. Second transformation is a dilation by a factor of, notice, I'm multiplying the x coordinate and the y coordinate by 1/2, but since it's combined with a reflection, that's why you notice that the y coordinate is also changing signs. Okay, so when I multiply A prime by 1/2, and then I flip the y coordinate over, I get 0, 1. So here's A double prime. B double prime will now be at -3, 2. And C double prime will now be at -6, 2. And I applied that transformation to A prime, B prime, C prime, and I called it A double prime, B double prime, C double prime. If you dilated a figure by a factor of 2, what transformation could you use to return the figure back to its pre-image? Once again, I talked earlier about how you just want to do the opposite of what you had just finished doing. So, dilate with a factor of 1/2. If you dilated a figure by a factor of 2 and then translated it right 2 units, what sequence of transformations would return the figure back to its pre-image? Translate left 2 units, and then dilate with a factor of 1/2. The student is asked to reflect a figure across the y-axis and then vertically stretch the figure by a factor of 2. Describe the effect on the coordinates. Okay, well, we know that the rule for a reflection over the y-axis is this. And if I'm trying to vertically stretch the figure by a factor of 2, that rule would look like this. So how could I take those rules and combine them together to make one transformation rule, it would be xy maps to negative x, comma 2y. The last kind of examples that you're looking at, you're just predicting what's going to happen. So it's saying if triangle LMN is translated along the vector negative 2 comma 3 and then reflected across the y-axis and then reflected across the x-axis, what would happen to it? Okay, so since this example isn't really doing the transformations, it's just predicting it, you might want to pause and just read their predictions before I go over example 3 part B for you. So square HIJK is rotated 90 degrees clockwise about the origin and then dilated by a factor of 2, and they've given a rule for that. Okay, so the effect of the first transformation is that it will HIJK will be mapped into quadrant 2. The second transformation is to dilate it by a factor of 2. So the effect of that transformation is it's going to stay in quadrant 2, and be twice as big, or twice the size of HIJK. And I think I accidentally answered the last question in this one. Pause the video for the your turn below.